Alright, so today we're gonna learn normal tangential coordinates. As simple as that, it just follows the particle. So if we have a trajectory right here and a particle, we have a position vector, alright, and we have two vectors, two important vectors, the normal and the tangential. The tangential vector always is tangential to the trajectory, so we can draw it right here. Okay, we have the tangential, and the normal vector is always perpendicular to the tangential, and so important, it always points inside the curve or the concavity, so it goes inside always, goes right here. What am I talking about? So for example, if we have a particle right here, the normal vector will be always here, the normal vector. If we have this, the normal vector will go inside the curve. It never goes outside the curve, all right? Okay. Now, another important thing is the trajectory as itself. For example, the particle starts its movement right here, okay? So it's the time 0, for example. This trajectory that follows until its last position right here, we are gonna call it with the letter S. All right, so it is called S, and we will have a huge powerful expression with this S related with the trajectory and the speed and the acceleration. So we have this S, the first derivative of S times differential of the first derivative of S equals the second derivative of S times the derivative of S. You know, saying derivative a lot of times is pretty confusing, it's hard, so just keep in mind that if you have a letter or a variable and then a point like this, a point means that it is the first derivative respecting the time, okay? So now I'm going to call it S point times differential of S point equals S 2 points times differential S. It's way easier to say derivative every 5 seconds. Okay, this is going to be a powerful expression, man. You will see in the following videos when we solve problems of kinetics. Now, what can we say about these two vectors, right? First of all, the speed, the absolute value of speed is only determined by the tangential vector. So we have this. The vector of speed equals the speed, I'm talking about the absolute speed times the tangential vector. And just keep in mind that I've been talking that S is equal to the speed and S 2 points equals the acceleration. Just like if you derivate a position, then you have the speed, and if you have the derivative of speed, then you have the acceleration. It's the same here. So we can put it as S point times the tangential vector. Okay? Now, this is about speed. What we have about acceleration? Let me see. Okay. As you may know, we have two vectors, tangential and normal, so we also gonna have normal acceleration and tangential acceleration. And they are represented in this. Acceleration in its complete way equals S 2 times, no, it's S 2 points, I'm sorry, times the tangential vector plus s point squared divided by the radius of that exact moment, right? The radius of the curve times the normal vector. So this is the tangential acceleration, and this is the normal acceleration. So we can put it in this way. Tangential acceleration equals s 2 points times the tangential vector, and the normal accelerations equals s point squared over the radius of the curve in that exact moment, because it can change, times the normal vector. Okay, so this is also pretty important, because the accelerations in NT coordinates, normal tangential coordinates, are so important because it will work for kinetics. We're going to find a lot of things with these two acceleration in kinetics. And there is also a theoretical important fact here. The tangential acceleration is absolutely responsible for the change of speed, right? Change of speed. And normal acceleration is responsible for the change of direction. So if you have, for example, a linear trajectory, just know that you won't have a normal acceleration, right? Because the direction is the same. And to finish, what do we know about the radius of the curve? Just know that if you have a curve right here, every point will have a radius. A supposed radius, yeah, right? For example, here you have this radius. If you are here, where's going to point your radius? To the other side, right? For example, it can be short, it can be shorter than the first. And here, the radius can be right here. How do you calculate this? Well, there is a big formula, and I'm going to write it. 1 divided by the radius equals the second derivative of y respecting x divided by 1 plus the first derivative of y respecting x squared. All that elevated by the 3 divided by 2. So you have this. You have something like this, a square root, and then at the third. And this is divided. So this is a huge expression. It's a bit complicated to see, so I prefer to do it this way. 1 over the radius equals the second derivative of f. You know that f is equals y, x. The function of x is equal f, also y. That is way easier to express it. 1 plus squared. I think it's way easier to understand this formula if you put it with f instead of dt, dy, dx. So this is everything you should know about normal tangential coordinates. And this is pretty important. Don't forget about this, because in some problems they will tell you, for example, this particle has a linear movement, so it will have a normal. a normal acceleration of this particle has a constant speed, right? For example, 5 meters per second. So if it is a constant speed, it won't have a change of speed, so you won't have a tangential acceleration, right? So it's pretty important to know this theory, and in the following videos we will solve a lot of exercises of kinetics, and you will see the huge application of this. So see you later, man.